everybody, it's me, Mario, and I'm Yoshi. And as you can tell, everybody, we have a plush upgrade. Yeah, we got our plush selves here now. Yeah, I'm a little bigger than I thought. You are a lot bigger. You're as tall as me, Yoshi. Yeah, I am. Anyways, everyone, today we're back at it again with another game theory reaction. Today, we'll be reacting to, Mario Odyssey's big lie? Power moons have no power? Oh, we're talking about the power moons again, aren't we? Yeah, saying they have no power? Wonder what that's all about. Anyways, let me just sit down. Yoshi, you don't mind moving over, do you? The audience kind of needs to see this too. Oh! Are you good? I'm fine. I might need a support or something. Alright, let me move over. I guess, is this good? I don't know, I'm a little bigger than expected. Okay, on the back. How's this supposed to work? I'm not sure. Are we gonna need our Lego counterparts for this? Probably. I think we're too big for the camera not to be blurred. Alright, pretty much. Alright. Woohoo! Where are you going? I'll be right back. Alright. Okay, here I come. Woohoo! I'm back. Why are you so much smaller now? Your turn, Yoshi. Alright. Whee! You coming? Woo! Ow! Ow! You good? Being big doesn't mean you stay fall. Ow! Oh! Uh-oh! Is the camera okay? Is it okay? Okay, the camera's fine. Anyways, let's get back into positions, Yoshi. Alright. Okie dokie. Let's go in 3, 2, 1.
Hello, Internet. Welcome to Game Theory. Can you finish watching this episode without touching a coin? No, you cannot. You know, over the years, we've explored the Super Mario verse from a number of different angles. We've looked at the sciences, from the biology and psychology to the physics and astronomy. We've examined the humanities through Mario's communist leanings and the economics of the Mushroom Kingdom's real estate market. We've looked at the heroes, the villains, the side characters, and the blurry lines that divide them all. However, after all those years of analysis, one question remains. Well, actually, a lot of questions remain. I could dig deeper and deeper into this series forever, but let's just say that one question remains for dramatic effect. One question remains. A question about the single most important item in any of these games. The driving force that compels Mario to go forth on adventure after adventure. Today, we're looking at the primary MacGuffins of this series, the Power Star. Or, more accurately, the Power Moon, since Mario Odyssey is the most recent and the most topical game. Seriously though, why is Mario collecting these things? What exactly do they do? In past games, it was always a bit unclear. Their power lets you open doors? Okay. For being such an overly elaborate locking system, it didn't really stop Bowser, did it? Super Mario Sunshine, they make the sun shine brighter. Awesome.
Now I'm thinking about it, do these things even have any significant power to them? I mean, the superstars give us invincibility, but the power stars?
Power moons and power stars are used as fuel. In Galaxy, the grand stars charge up Rosalina's space station. In Super Mario Odyssey, the literal butt-ton of moons that you collect are the gas that enables you to chase Princess Peach from kingdom to kingdom. Which then
they have to have an immense amount of power.
Are power moons. If these moons can truly fill an airship's gas tank, how much punch does each one pack? For the lengths that Mario goes to collect these things, they must be pretty darn good, right? right? Oh, dear sweet summer theorists, you don't know the half of it. But you will in a little over 10 minutes. So how do we determine how much energy is contained in each individual power moon? Well, my first impulse was to see how many moons it took the Odyssey to travel any set amount of distance. The problem is, the number you collect in the game doesn't correspond to actual flight power. For example, Mario only needs 5 moons to travel from the Cascade Kingdom to the Sand Kingdom, but he needs 20 to reach the Snow Kingdom? It's arbitrary. And then, once a kingdom's visited, Mario can just return as often as he wants without needing any additional moons. Conservation of energy much, guys? Imagine if your car required an increasing amount of gas for each new city that you visited, but then you could return to the previous cities without burning through any fuel. Forget plumbing, Mario's got himself a future in perpetual motion machines. Lucky for us though, moons are shown as a power source in not just one, but 2 different locations. Sure, there's the Odyssey spaceship, but in a mission midway through the game, we see them as a fuel source in the bowels of the Metro Kingdom. A mid-game mission requires Mario fix the power plant that drives New Donk City, and, as you can see here, full power moons enter the reactor, and empty power moons are dispensed on the other side. Timing it out, this generator...
Apologies everyone for us not really talking. We're just processing what's going on. Yeah, we're just trying to process all of this.
Your kidnapped girlfriend. It's uncomfortable to see so many moons just sitting there, right out of reach, and then getting devoured so quickly by the reactor. Screw New Donk City, Mario. Break that pipe, grab yourself the 124 moons you need. Seems like they have plenty to spare, and go save your girlfriend. Talk about speed runs. The game would be over in a little over 2 minutes. Anyway, we're told by Mayor Pauline at the start of the mission that the power plant is necessary for the kingdom's festival. Now, that's a bit unclear. Is it only generating electricity for the extra lights of the festival? Is this the only power plant in the city? Does it fuel the section of New Donk City we play through? Or is it responsible for this whole city that we see surrounding the play area? Unfortunately, Nintendo, for some reason, didn't program functioning electric meters for every building in the game, so we're gonna have to make a few assumptions here. First, let's assume that this is the only power plant in New Donk City. Now, we know for a fact that that can't be true, as prior to this mission, we see devices that are actively using electricity, including stoplights, marquees, and even the stage lights inside of City Hall. And when we first get to the kingdom, we see the entire city lit up in the night sky, so something has to be giving these buildings the juice. That said, though, we can balance out that first assumption by making a second
Mario, I
one.
got a question about the power that's going on in New Donk City. What kind of question, Yoshi? How come the robotic wiggler was draining the power from the top of City Hall and not from the power plant? Honestly, Yoshi, I can't really answer that. I really don't know why. I don't know why it wasn't draining energy from the power plant instead of from the City Hall.
It's giving power to only the playable areas of New Donk and ignoring the outskirt territories we see in the distance. We're underestimating its potential energy output. So in total, it should give us a reasonable approximation. With all that out of the way, we can now...
I mean, New Donk City is based off of New York City, so I'm pretty sure the energy would... Whatever the energy rate is in New York is the same for New Donk. Pretty much.
700 square meters, while the eastern platform measures 1,090 square meters and the southern platform 2,025 square meters. In total, the explorable area covers about 39,800 square meters, or around 10 acres of land. That's about the size of 2 big city blocks in New York City. And speaking of New York, I'm going to go out on a limb and say that New Donk City has a similar power consumption density as the real-life New York City.
Called it.
New Donk is clearly inspired by New York. If the names weren't obvious enough, look no further than the New Donk City Hall, which is modeled after the Empire State Building. Both cities feature a relatively even mix of skyscrapers, high-rise developments, industrial buildings, and public parks, and they even have a similar population density, with around 10,000 residents per square kilometer. And you might think that I'm making that up, but I'm not. I put put my census-taking skills to the test and counted how many residents are in New Donk City, and the math checks out. And I point this out specifically because I know a lot of people out there give us crap when we make mistakes, but I hope you realize how hard we're trying here. We literally counted everyone in a fictional city in order to scale to the population density of a real-world locale, all for the sake of measuring the fictional energy output of a fictional power generator utilizing fictional moon fuel. If that doesn't deserve a subscribe right now, I don't know what does. It gets even more ridiculous. Thanks to New York City's Local Law 84, the Mayor's Office of Long-Term Planning and Sustainability releases an estimate of energy consumption.
I just want to know how much energy the power moons are packing, because if we know how much energy they're emitting, then we'll know how much energy the power stars are emitting. Yeah, that's true.
So let's simplify things a little bit.
Also, how is Rosalina with the Grand Stars? How is she? Oh, honestly, I can't really tell. It's been a long time since I last saw the observatory. So I can't really have a definitive answer for how exactly she's doing, but I'm pretty sure she's doing fine.
So the city is using 3.3 billion LED light bulbs of energy per year. According to the U.S. Census Bureau, New York City has an area of 783.8 square kilometers. So dividing the total energy consumption by the total land area provides us with the average power density of the city, which comes out to be 42.56 watts per square meter. Multiply that by the area of New Donk City, and we finally arrive at an estimate for the city's total energy consumption of 1.7 megawatts of power used by New Donk City per year. Again, meaningless number. So let's try to turn them into something that makes a little bit more sense. The problem with watts, and the reason no one can ever read their own electric bill, is that they're a rate. They measure energy consumption over time. I mean, seriously, if you look at your electric bill, or you buy an appliance and it's like, this refrigerator uses 200 watts of electricity per year. You're like, sure, I guess 200 doesn't sound that big. It's not like a million, so I'll take it. Well, what that watt number really means is that refrigerator uses 200 joules of energy per second that it's turned on and plugged in. And you're like, whoa, hey now, that seems like a lot of energy. 200 joules per second. Maybe my Go-Gurt doesn't need to be that cold, you know? But before you start defrosting the thing, turns out it's not that much energy. In fact, the energy in a single calorie of food is over 4,000 joules. So the energy needed to power that refrigerator is nothing compared to the energy from the food that exists inside of it. So if joules aren't that much energy, then what does that mean for our power moons? Well, they're still stuck in useless watts over here. So if we're gonna make anything of them, we gotta convert them to a more useful unit. So a watt equals a joule per second, right? And it just so happens that New Donk City consumes moons at a rate of exactly 1 per second, which makes the math really easy. 1.7 megawatts of energy equals 1.7 megajoules of energy per second, times 1 second just equals our total number of, drumroll please, 1.7 megajoules of energy per moon. Now again, that may seem like a lot. It's got the word mega in it, so it must be good, right? But going back to our calorie example, 1.7 megajoules is around the amount of energy that you get from eating a medium fries at McDonald's. Carrying it even further,
wait,
to power your own
what?
body for a 2,000 calorie per day diet,
What?
you'd need to consume
What does
5
it mean?
power moons every day just to get enough energy. So I may have been predicting that power moons would have the energy of a nuclear bomb at the beginning of this video, but all they really have the power to do is give you a nuclear tummy ache. It's no wonder Nintendo literally crammed these things everywhere. Here we all were thinking that this was some sort of special collectible, when in actuality they are no more powerful than a candy bar or two. Throw another 500 Snickers bars into the Odyssey, kids. We're flying to the moon. But this seriously can't be right? It is such a low power level. It's under 9,000, which is why I wanted to verify this math using a different technique, by trying to figure out the composition of the power moons. You see, in version 1.2 of Mario Odyssey, Nintendo added a neon filter to the game. Now, that might not seem like such a big deal, just some cool filter to make everything look like
So the power moons
Earth-bound
don't
inside
have
was
that
one of the
much
coolest
energy?
levels in all of gaming history, but if you
That's
dive
a bit of
little deeper into that
a
neon
bit of a
filter,
lowdown.
you discover something that's pretty interesting. Take a look at what happens when I point the in-game camera at the sun and then turn on that neon filter. For some reason, the sun appears blue rather than yellow or orange. Why would that be? There's actually a shocking reason. You see, in real life, scientists use a tool called a spectrometer to determine the composition of light emitters. Spectrometers work by using a lens to filter light through a prism, which then separates the light into individual wavelengths across the electromagnetic spectrum. This tool is super cool and super useful because each chemical element emits light at a unique frequency when it's excited. These unique wavelengths are called its spectral signature, because just like a real signature on a document, they are unique to whatever produced them. For example, if we have a faraway star, we can compare its spectrometer reading with the known wavelengths of the elements we have here on Earth to determine what elements that star is made out of, which then leads us back to Super Mario Odyssey. Why would the sun in the game produce this specific shade of blue or teal? Well, many stars, including our sun, are made of mostly hydrogen. And if you look at the spectral signature of hydrogen, one of the most prominent wavelengths produced is 486.1 nanometers, a wavelength of light that produces close to the exact shade of teal that we're looking at in Odyssey's neon filter, which honestly is mind-blowing. I mean, think about it. Someone at Nintendo actively programmed the neon filter to turn light blue when it was directed at the sun. Either this is the randomest piece of Mario trivia ever found and is a complete coincidence, or it was intentionally added to the game as a nod to real-world science.
Mario?
Now let's look at the moons. In general, when you look at any power
Yeah,
moon,
Yoshi?
the neon filter primarily shows you the
Pause the
color that
video.
corresponds.
What's wrong? Behind you. Behind me? Hello? Well, what the? Plush me? What are you doing here? I thought you were just a power-up or something. Nope, I'm real. And so is Plush Yoshi. But he kind of took a fall and he's unconscious, but he'll be fine. That's probably my bad. No worries. But what exactly are you doing here? I wanted to congratulate you two on the series. Sorry we kind of asserted ourselves in the intro and your thumbnail. Oh, right. It doesn't matter. I mean, you're still technically part of the video. Yeah. Anyways, I'm gonna go check on Plush Yoshi. So enjoy the rest of your video. Woohoo! Yep, that would be Plush me. Plush me and Plush Yoshi will be joining us in the series, either to be our replacements or just there to be fun. I really don't know. I don't know either. Well, let's keep going. Alright, let's go.
Each kingdom. Green for the Sand Kingdom, pink for the Lake Kingdom, blue for the Wooded Kingdom, and so on. However, the moons also are surrounded by these colored sparks, and it makes sense that these sparks relate in some way to the composition of the power moons because the colors appear consistent regardless of what kingdom they're found in. So, using the neon filter, I took a screenshot of a few of the moons surrounded by these sparks and then uploaded those photos onto a computer. I then used an eyedropper tool to find the specific hues of the four colors that you see emanating outside of the moon, specifically red, yellow, green, and blue, with wavelengths of 700 nanometers, 585 nanometers, 500 nanometers, and 485 nanometers respectively. And wouldn't you know it, this almost perfectly aligns with the four largest emission signatures of the element helium. Now, helium itself is a noble gas, and therefore it doesn't form any significant bonds that could hold energy. That said, an isotope of helium could, specifically helium-3. Now, the interesting thing about helium-3, it's very rare here on Earth, but it's believed to be abundant on the moon. More importantly, it's been theorized as a possible source of nuclear fusion. In Super Mario Odyssey, Happy hints that power moons and power stars are made of the same material, saying, apparently power moons come in other shapes. I had no idea. This would explain why power stars in Super Mario Galaxy form a sun in the center of the Comet Observatory. In order to harness the power of helium-3 that exists within the power stars, and
They're made of
they have
helium-3?
to undergo a fusion reaction. And that's also the reason they're so weak in the Metro Kingdom. Humans don't understand fusion, but future Space Princess Rosalina over here does. Meaning that there may just be more power hidden inside these things than we originally thought. We just need to unlock the power of fusion to get there. Until then, we're just gonna keep using them as glorified keys. But hey, before we end today's episode, I have a quick announcement that's your
So apparently the power moons and power stars are related.
Apparently so. And then not only that, but they have the ability to cause, like, nuclear fusions or something?
Pretty much. That's very interesting. Huh. Now it makes me wonder why I don't carry power stars on me all the time. If they have that much energy, then why not have some?
I think that's because we're left with the invincibility stars. I think that's why we don't have any power stars.
Oh yeah, you're right. But anyways, thank you guys so much for watching our video for today. Be sure to like and subscribe to the channel if you enjoy our content. Don't forget to hit the notification bell and leave your thoughts down in the comments. And also, as a quick reminder, our holiday specials are coming up very shortly. We'll see you guys there, and we'll see you in the next episode of Mario and Yoshi Adventures. See you next time. Bye-bye.